All right, let's get started. So we're going to be going into smart contract security today. Security is a pretty big part of programming on blockchains. So let's talk about like the general overview of what this like means. So security on like a blockchain platform basically means that you're referring to an exploit on the protocol level, i.e., you're referring to like the clients that people run on the network, or you're referring to the application layer, which basically is like the Solidity contracts that are being run on the blockchain. So the publicity of a blockchain really does expose the attack surface because everyone's public and all the actions that are happening on the network are public. So in most cases, for normal systems, for non-blockchain systems, usually you don't see the server side of the code exposed, right? Like you go on Facebook, all you see is that information that they present to you. All you see is like the user interface, but you don't really see like what they're querying, how they're querying it. Here you see like the Solidity contracts on blockchain, and basically you can look at these contracts and see what's going on. So you have an idea of how their backend essentially works, whereas in a normal server you don't. So again, the Turing completeness, we've gone over this a few times, but this greatly increases the attack surface because you can essentially run any program that any other programming language can run. So this versus Bitcoin, for example, is going to have much more exploits that you can go through. So this is going to require a different like philosophy behind development. So it's really similar to hardware programming in the sense that it's pretty volatile in how easy it is to like screw up. And I'd say Ethereum is like alpha software at the moment. None of this stuff is like ready for like true production, in my opinion. So if you're like an enterprise entity, I actually don't think blockchains are like ready for that yet. Any like questions? Okay, cool. So what can you like afford to lose when people are like trying to hack you on this like system? So people can drain like millions from your accounts. And this has happened like several times. People find bugs in smart contracts and they'll essentially go to those accounts and like completely like drain them or drain them part way. And people make a lot of money off this. It's like a public bug bounty essentially. And it pays a lot more than a lot of other exploits out there because your Ether assets are like immediately liquid once you have them. So contracts are actually like pretty hard to like change like afterwards. Like in fact, they're like nearly impossible to change afterwards. You can find workarounds to kind of upgrade your contract, but you can't really like stop like something once it's like placed on chain. So like suppose people have like are using a multi-sig wallet like contract that's been used by like multiple exchanges or like individuals who want to make use of a multi-sig wallet for security reasons because they want to have like M of N signatures in order to access their wallet, right? So people are going to deploy a contract on chain, and if this has a flaw, there's no way for them to be able to govern the updates across all those deployments of those contracts. Does that make sense? Okay. So therefore, it's like pretty imperative that developers are essentially writing like very robust contracts before they go on chain. So here's like some hacking history. We'll dive a bit into like the hacks themselves, but also like cover them on high level. So many of you have heard of the DAO. Happened last year. So DAO was the decentralized autonomous organization. The idea was that you'd raise Ether, and basically it would give you tokens to vote on what to fund. So if there were cool projects out there, you could direct your vote towards funding that project using your votes in DAO tokens. So what happened was a total of 3.6 million Ether got stolen, which was 70 million at the time. And that was a huge portion of Ethereum's market cap. So this was like a year ago, back when Ethereum was, I don't remember the market cap off the top of my head, but it was much, much lower than it was now. There was that craze that like around summertime that kind of like brought this like Ethereum like to be well known. But back then it wasn't as well known. Yeah, and now it's like $400, so it's like 40x in terms of market cap, which is pretty crazy. So the attackers ended up like withdrawing ether from the DAO contract through using like the DAO tokens, and there was an exploit known as a reentrancy exploit. Nick will cover that more in depth, but the idea is that basically the attacker was able to ask like the smart contract to give back ether multiple times before like the contract would update its own internal balance. So this was made possible for two reasons. One is there was on the split DAO function, which basically there's like principles of a DAO that you can like look at, but the idea behind split DAO is that if you want to, for a DAO, you put your votes in, but if the DAO doesn't go the way you want to, then you split the DAO off into a different DAO. It's a little bit confusing. We won't cover it in this lecture, but there will be articles that kind of like tell you about how all this functionality works. But basically, there was a problem with the split DAO. There was a problem with the split DAO function from the withdraw reward for function, and this would allow you to withdraw 30x as many DAO tokens that you should have access to. But then there was also a non-recursive attack from split DAO through the transfer function, and this would allow you to double your tokens like every DAO split. So basically, with a combination of these two flaws, you would be able to withdraw 30x as many tokens, and you could do this like as many times as you want. So the result of attack was a hard fork, and basically the new Ethereum that we have now is not the same as the old one. So since the hard fork, the attacker, he basically ended up making off with his Ethereum Classic, which means he got away with about 67 million, but he hasn't like cashed all of it out. Like he's shapeshifted some of it. Shapeshift is basically a platform that lets you like take tokens and like instantly exchange them for like other tokens. It's like a centralized API, but they claim to not keep track of any information, so they weren't able to like expose this guy. So in this hard fork, in this like hard fork, basically what ended up happening was the transactions related to the DAO were reverted, and those were the only transactions that got reverted. So the rest of the blocks that ended up going on chain were not reverted. Everything was continued after that, but the ones related to the DAO were reverted. So what about the hacker? Like what happened to him? So there's like some rumors about about the hacker and like what exactly happened. For example, like why did the hacker only take like 1/3 of funds? It's speculated that he ran out of gas. He also heard of like maybe plans to like fork, and he was hoping that the fork wouldn't go through. Maybe that was because that's why he didn't like. That's why he only took like 1/3 of the funds, because if he took all of it, it'd be a lot more of the market cap, and that would be like that would incline the foundation to take more like harsh steps towards the fork. So it's also possible that the hacker like shorted DAO tokens. So then he made like money like during the hack. But yeah, basically like there's a lot of rumors about what happened, and people aren't sure like what the hacker's incentives were. So the SEC actually recently ended up ruling that the DAO may have been in violation of like securities law, but there's like no word on like whether it's legal for the hacker to just go out and steal like all these funds. Like the government doesn't have like really a stance on this. So he essentially got away with 67 million. Yeah. So there was another hack. How many of you guys have heard of Parity? Okay. Does anyone want to explain what like Parity is? Okay. Parity is basically an Ethereum client. It's written in Rust. How many of you have heard of Geth? Yeah, Geth is basically the Go version of the Ethereum client. This is simply the Parity version. It's supposed to be like much faster, much like cleaner code. They also have like a multi-sig wallet contract that they wrote for like people to store money on if they're like mining using that client. So for multi-sig, like in Bitcoin, generally like this is done like off-chain, but on Ethereum it's done on-chain. So you have contracts that make it really easy to write multi-sig on Ethereum, but for Bitcoin it's much more difficult. But there's a trade-off here, because if you're like putting your multi-sig contract on chain, then it's much more prone to bugs, right? But if it's off-chain, then nobody like knows what's going on. So this was a simple attack that allowed the hacker to take ownership of the victim's wallet with a single transaction. I've left like an Etherscan link for those of you guys who want to check it out like after the lecture. But basically there were 3 victims that were like focused on for this hack. So there was Edgeless Casino, there was Swarm City, and there was Eternity. And you have to keep in mind that a lot of people actually use like Parity Wallet to like store their money. So that means like exchanges, that means like other ICOs, that means like any other like big entity that like trusts like Parity, because there's actually like very legit people on that team. Like for example, Parity is actually led by Gavin Wood, who wrote the Ethereum Yellow Paper, and he's no longer part of the Ethereum Foundation. This is like his main cause. So you'd imagine why like people actually like trust Parity to be like the best of the best, because they're also writing like their whole client in Rust and everything. So these guys are actually like, really like solid programmers. I mean, I personally trust him. But after this happened, it's like, who do you trust to like write like secure contracts, right? So 153,000 Ether was stolen in this attack, and that was like 30 million. But then like some white hats actually like came in and they saved like the rest of the money that was on the network. So that means $78 million worth of tokens that were using the Parity multi-sig wallet were like saved. And also about 377,000 like Ether was also saved by white hat hackers. And these white hat hackers actually were at IC3, which was like the conference that me and Nick went to like over the summer. And they just like spent a day just like saving the day. No one really like knows what their incentive was like to do it. Like I guess they really care. Like there's a lot of altruists in this space. Like I think a lot of like networks like survive because there's like people that want to like make this thing thrive. Because if they didn't come in, then somebody could have just gone in and stole the rest of the money, and it would have been like a DAO 2.0. But because they came in, it wasn't a DAO 2.0. They also saved like some ICO projects like BAT, Economy, and some others. So basically, yeah, they saved 150 million. That's a lot of money. So what happened with Parity? Basically, so you see here, there's like one small change on this git diff. It's literally just like the internal modifier, but it's a little more complicated than that. That wasn't just the only thing that changed. So the idea behind this contract was basically you have a wallet library and you have a wallet, and you make these like modular and like call to each other in order to save gas. I'm going to move over this pretty quickly because you guys are going to have like a reading that tells you more about this, but basically the wallet contract was heavily dependent on delegating calls to the wallet library. And delegate call basically lets you call an external contract, but it has a few like differences / key things to know about it. One is it lets you call the contract while preserving that call context of the current contract that you're in. So if we have a message.sender that we're looking at in the current contract, and we delegate that call to another contract, you're referring to that message.sender inside the current contract's context that you delegated the call from, not the contract that you're delegating the call to. So this is like similar to bind this in JavaScript, which basically lets you pass in the current call context of a function that you're in to another function. So this is like a completely like reasonable like utility to have. So what like kind of happened with this? So the problem with Parity was that the init wallet like class constructor didn't have like a guard modifier. So basically, it didn't check if the wallet had been initialized. So it didn't really like keep track of like the owner like initializing like the wallet more than once, right? So you could just keep initializing the wallet. So if you could call it again, you're basically like exposed. So the second problem was that there's this idea of derived contracts, basically that in this case, the wallet contract is created by the wallet library. And this means that the wallet can call the init wallet function. But because the function was not declared internal, the init wallet function, that means any derived contract of wallet can then call the init wallet function. So since we use delegate call, if the attacker calls the init wallet function, then the context of that call would be from the attacker's address. The third problem was that in the wallet contract itself, they're using a fallback function as some kind of like catch-all for all the delegate calls functions to the wallet library. So this creates an attack vector into the wallet library from the wallet contract. So therefore, we have like a way to then publicly access the init wallet function from the wallet contract. So that actually calls for a lot of trouble. So walking through the attack, when an attacker calls wallet.init wallet attacker, the wallet's fallback function is then triggered. Then the wallet's fallback function goes to delegate call to the wallet library. And then that call data from the delegate call will consist of the function selector for the init wallet address function and the attacker's address as the argument. So then wallet library is going to receive that call data, and it finds that its init wallet function matches the function selector, and it runs init wallet on the attacker's address in the context of wallet, setting the wallet's the owner variable of wallet to the attacker. And now the attacker is the wallet's owner, so therefore they can withdraw any funds at his or her like own leisure. Does that like kind of make sense? So what we can conclude from this, writing smart contracts is hard. This like wallet was written by Gavin Wood, right? Like he literally invented like this whole system, but even he was like prone to like messing it up. And this was also like looked over by a few people in audits, maybe not as intensely as it should have been, but yeah, this really calls for a lot more due diligence on these contracts. So in reality, like this whole like demo that I did was like much more simpler than like what the real contract is, but the ideas are like the same. You were able to just take a delegate call function and eventually hijack the owner through a derived contract of wallet. So from what we can get from this, Solidity is like pretty messy in design, right? Like, why isn't it doing like private functions by default when we're dealing with financial assets that are worth like millions of dollars in some cases? Why aren't we like requiring guards to all functions? Like, there should be like a very like strict language. And there's language philosophy out there that, like Ruby, for example, like you can like type stuff up and it like automatically just works somehow. It's very like clean of a language, but it sacrifices that robustness in exchange for like the easiness of the language. Solidity should probably do something different. They should be much more strict about how you write contracts. They should require that you write a lot more code in order to make sure that it works the way you want it to. So I think another solution to this is that you make contracts much more simpler, because had they just put everything in one contract, they wouldn't have run into this problem with delegate call. So the internet is actually like full of code like this at the end of the day, but here there's like there's like a huge liquidity pool, and basically if somebody gets a hold of this ether, like they can make $30 million just by like doing a simple hack. Like what I showed you there wasn't like that difficult, right? Like if you just poked at it enough, like that $30 million would have been made to you in like maybe a few days. So that really does mean that we need stronger security audits. So the takeaway from this is that only you can really stop DAO attacks. You need to be like very careful about how you write these contracts. And here's some things to keep in mind. So this technology, it's highly experimental. Things are being constantly updated. There's going to be like a hard fork, for example, in I believe like October 13th or something. It's going to like add some updates to Solidity. Those are going to like change some things and deprecate some things that in previous contracts that they won't like work the same way they did. So if you're doing like Pragma Solidity like greater than on your like contract deployments, basically like if it selects a greater version than the previous one that you had, if it selects the most recent version, like things might not work the same way they once did. So that's like a huge problem. Another thing is that you need to prepare for failure. At any moment, like in any contract or method, you need to be like ready for like something to fail. So you need to write a lot of assert statements, require statements, modifiers, make use of all of those. You should roll out carefully. So like if you do an ICO, have bug bounties, because you can either have a bug bounty at the start and be generous about it, or you can have a hacker just have his own bug bounty and take advantage of your tokens. You should keep updating with like the community and software, because it keeps moving. Like everything keeps moving fast. I think Ali, he can definitely like speak to it, because he's the main developer, and he definitely sees like a lot of changes coming all the time. Yeah, so you really need to keep in mind like the properties of a blockchain, whether it's public or private, and you need to also understand like there's a difference between send and call. Nick will cover that again, by the way. Basically, you should also ask if simplicity or complexity is better. So whether you want rigid or upgradable, with rigid contracts, these are easy to like maintain and protect. If they're upgradable, these are killable, and these are modifiable, but basically they add on additional attack vectors. There's also monolithic versus modular. Monolithic is basically when you do your contract storage and methods with locality. Modular basically means that you are abstracting contracts and you're using different like separate contracts, like you did with like the Parity wallet, for example, and you're basically trying to link them all together. That's like more complex, but it makes them more, I guess, easier to understand in some contexts. And duplication versus reuse. Basically, you can either roll your own math functions that are cheaper on gas, or you can just use the Open Zeppelin ones that are expensive, but they're at least maintained, and they're like usually guaranteed to work. So I'm going to hand it over to Nick for some more common attacks in detail.
One of the most common attacks here is what's called a race condition. People also call them reentrancy attacks. And what that means is that you can run a function, and as the function goes through execution, line by line, someone can run it again, right, before it finishes. So can you spot some egregious error that might happen if you run this function withdraw balance multiple times before it's finished? Could you speak louder? You get the DAO attack. How do you get the DAO attack? Bless you. Yep, exactly. So execution will go through. It'll reach this if statement where it's going to send, and the send might be successful, right? But when it sends, the second execution of the function will also get to the send. And so before getting to the 0, where you set a user's balance to 0, they might then get double the amount because it executed twice. Does that make sense? Right, okay. So do you see where it says message.sender.send amount to withdraw? Yes. Okay, so that's an execute to send an amount. And so what someone can do is they can run a function, the withdraw balance function, and it can get to that, and that call will succeed, right, if they have enough money. And before it moves on to the next line where it sets their balance to 0, the second call of that function will also get to the send. And they'll also receive like a second amount because their balance still hasn't been withdrawn to 0. Does that make more sense?
So I mean, this is like within some smart contract that someone has written, right?
Yeah.
So like, how can they make this? How can they make this happen twice?
Just
they're calling this.
Yeah, they call it twice. Yeah.
So it's just running in parallel, like calling the same function.
Yeah, and you can do that by say executing another contract and having a loop on that contract that calls this function.
So you don't have to run in parallel, you just run a loop on.
Yeah, you can just do it in a loop, and because it's asynchronous, the way it happens.
Are contracts always asynchronous?
So they shouldn't be, but you can assume if there are multiple calls that they're not going to run like one after the other. They're going to run at different times, right? Because they're different calls.
Why does the second call get executed before the user bounces to 0? Like, shouldn't the whole project
Yeah, but so they're called from different locations, right? So you can imagine a contract calling the code, but imagine what would happen if you had to wait for every other contract to execute. So say I'm user A, and you have user B, right? So I call the function as user A, but user B also wants to call the function. User B shouldn't have to wait for me to finish running the function before they can call it as well, right?
But isn't that just a consequence of like deterministic logic? That's what it has to happen. Because like it's actually executed when it gets minus window. When that transaction gets like put into like a block, that's when like it's executed, right? So how could it like how could two just execute the same thing?
Yeah, I'm not sure I'm understanding where we're going with this. But so talking at the end, we've got like a bunch more attacks to get through. Yeah, yeah. So that's the issue. But over here, so this is the solution, right? And how does this fix the solution? How does this fix the problem?
Well, their balance is always put to 0 before any send.
Right, right. So even if you call it multiple times, by the time the second call gets to where the previous reentrancy attack occurred, the user's balance is already 0. So they're just going to withdraw 0. Okay, a lot of questions. Okay, just save them for the end. Okay, second method of fixing reentrancy attacks is implementing push over pull. And what we mean by that is when you have a pull vector, that means that the user has the control, right? When you have a push vector, that means the contract is the one that with the control. So, for example, over here, you have an auction contract, and people can bid, right? And the highest bidder is assigned on the state variable, highest bidder, right? And what can happen is you can have a contract that's what we call poisoned, and that contract cannot receive funds, either by a fallback function or some mechanism like that, right? And so if the contract sends funds and becomes the highest bidder, what then is the attack in this situation? What happens here? So the poisoned contract is now the highest bidder, right? But it cannot receive funds. So can anyone spot where the attack would occur?
Well, I mean,
Oh.
so,
Yeah, whoever, it's fine. Okay.
well, so the if highest bidder got send highest bid is going to fail in that case. But still, the individual is going to be the new highest bidder.
So
Future calls. Or the poison contract is going to be the new highest bidder.
yeah, so I think you're on the right track. So if you take a look at where the highest bidder assignment is happening, it's after the throw. Right. So if the highest bidder, if someone else makes a higher bid than the poisoned contract, they're trying to become the highest bidder, right? So they'll go through this, but the highest bidder.send mechanism will fail, right? Because the contract can't receive their previous funds. Because, okay, so the way this contract works is for a new person to become a highest bidder, the previous highest bidder has to receive their funds back. And so it'll throw every time because the send will fail every time. So that means that the new person trying to become the highest bidder can never become the highest bidder because this line right here will never get executed. Does that make sense?
How does the contract poison?
So you can just run it with a fallback function that can't be payable. Yeah. Poison sounds really kind of like extravagant, but it's like really simple. Yeah. Okay.
Is there any way to ensure that a bidder is an actual human and not a contract address?
That's a good question. The nuances of contract addresses versus COAs. I'll look into that and get back to you. Okay, and so the good solution, right, to this is implementing a push mechanism. Yeah.
You might be able to check that with message.sender versus transaction.origin.
Okay.
If they're different,
Maybe. I'm not familiar with transaction.origin, actually.
that gives you like the last contract that belonged to you. But the chain had to be started by
Okay. All right. So the push mechanism here is, so the pull mechanism is when the external actor, which is maybe a contract or a human being, is making the call, and so they have the control, so they're pulling, right? Where the push moves that control onto the contract. So here we have a situation where we're offloading all the withdrawal mechanisms into this mapping, refunds. And so when someone else becomes the highest bidder, it doesn't matter whether or not they don't send immediately, right? It's reassigned into the mapping. And then if a person wants to withdraw their bid, then they can go to the mapping and withdraw it. And in that case, if you're a contract that can't receive payments, then your withdrawal will fail, but nobody else's will. Okay. No questions? Perfect. Okay. Last solution for reentrancy attacks, locks. And what locks are, I think this is the most intuitive part of the solution. You have this variable called lock balances, and you set it to true at the start. And so you have this if condition that'll never be fulfilled while lock is true. And then at the very end, you have to set it to false again, so that the next person can run the method. Yeah. What could be an issue with this? Maybe not this specific version, but what is the most important thing here in implementation? I guess if I had to point to a line.
That just one sender is in the same line.
Yes. Okay.
They actually, the logs prevent the other senders to
Right.
to the same.
Right. But so if I implement a lock, what has to happen? Like after the lock has been set to true, what do you have to make sure to do at the very end?
Like
Some people.
allow other senders to go into the
Yeah, exactly. Or else the contract becomes useless if the lock is permanently true. So you have to remember to set it to false. And you have to watch out. There's some situations where it can throw halfway through, right? Or it can just fail halfway through. And in that case, the lock just never reaches the true condition, the false condition, and the lock is never reset, which makes everybody sad. Okay, so other stuff you can do is you can check how long it's been since a certain method has been run. So you can say, okay, I'm gonna run this and record now, which is a timestamp. Remember, timestamps can be manipulated by miners, so you generally don't want to use timestamps, but it is a valid way of making sure reentrancy attacks don't happen. And you can set the limit to be, several days after the fact, by which time somebody else can then call the method again. And this is what you'd use. Keep in mind, you can just directly call 1 seconds, right, or 60 seconds, or 60 minutes, right? Just literally put the word after the int literal, and you'll have that denomination of time. Watch out for leap years and stuff. Those get strange. Generally, a year, like these are the correct conversions. Okay. Integer, overflow, and underflow. We talked about this last time. If you're sending someone, say you're using a uint256, and you're sending someone an amount of 2 to the 256 minus 1, right? And I don't know why you'd send that much ether, but you do you. But say you want to add an additional ether to that, right? well, now you're sending them like 0, right? You're sending them a grand total of nothing. And you don't want your contracts to be doing that, especially when you're not using, because realistically, contracts will never send the maximum amount of uint 256, right? But if you're using uint 8s, tragedy can ensue. So watch out for that. Always check for overflow and throw if it's not the correct amount. If you're sending less than the original amount, and that's how you check that over there. Yeah. Keep in mind, you can also force send some funds to a contract, even if it's not payable, even if it's poisoned, like we talked about earlier. And you can do that by self-destructing and having a victim address. And so what that means is you self-destruct a contract, which is just a genuine call for contracts, pretty useful. But you put an address in there, which you generally don't do. And what that does, it says to the contract, okay, send all the remaining funds in this contract to this address. And whether that address likes it or not, they're going to receive those funds. And generally you think, wow, free money. What's bad about that? But there's some contracts that are not built to receive funds, right? There's some contracts that don't expect funds to be sent to them. And when funds are sent to them, that sets off a whole cascade of events that might lead you to be very, very unhappy. So the general takeaway here is that when you're designing for security, you don't want to be defending against, you don't want to only be defending against like incredibly smart people, but you want to be protecting the unexperienced contract writers who don't prepare for situations like this. And this is the rationale behind that. Okay, so time to sign in. You can take a picture. It's just tinyurl.com, devdecal4. One word, code is underflow. Oh, overflow. Jeez. Okay. Engineering techniques. Okay, simple stuff. So what can happen with division, because Solidity is Solidity, with all its quirks, and we just love Solidity, right? And so when you divide, it's actually a florative, right? So when you divide 5 by 2, it'll result in 2. Understandably, that makes people very upset when they want denominations of a certain number. What you can do to tackle that, don't divide. If you need to divide, use a multiplier so that you stay within the realm of integers. So in this case, you'll multiply 5 by 10, so you have 50, and then divide by 2, 25. Or you can keep track of the numerator and denominator as like an elementary fraction, basically, and carry that through the entire calculation. Both are not convenient ways of doing things, but hey, this is Solidity we're talking about here.
Wait, is that an attack vector?
It's just good practice, generally. It could be, though. If somebody sees that you're dividing, they can take advantage of that. Okay, so we've talked about this. All data is public. Think about a game of rock, paper, scissors, where people are playing with money. And so player A sends in their move, maybe rock. Player B just waits until player A sends in the result, checks the bytecode, sees their move, and then plays against that, right? Super easy to do. So what you want to have happen is you want to hash, right, each of the moves, and then put them on the blockchain, and then submit moves, and then check that the moves really were what they said they were, right? But there's still an issue with that, right? And it's that people can still see the hashes, right? Well, more directly, right? If you do the hashing on chain, people can see what the input to that hashing was, right? So that's a problem. But also in a game like rock, paper, scissors, where you only have 3 moves, it's not that hard to hash each one. Check what the hashes are, unless you don't know the hash function, in which case, just try different hash functions. There aren't that many. But yeah, does this make sense?
Wait, can't you do something like a NOS where you add it to,
When you add,
like, can you add like, wasn't it like salt to your input to make it more unique so that it's not only 3 variables, but you can still check.
but how would it be self-verifiable later on? It needs to be verifiable by both parties. Afterwards, after the fact.
Can you just tell them the salt then?
I'm sorry?
Yeah.
The salt?
Like a key, for example, basically.
Okay,
Think about like a private key that you would send a second message afterwards. They would have your key,
Mhm.
and you can't predict like how you would hash your same key
Yeah,
to a
that's
different
fine.
value. So
Yeah, that's actually called a commit reveal.
Yeah.
commit reveal.
Yeah.
Oh, okay.
There's actually like mechanisms, like actual functionality in Solidity for that.
Oh,
Okay.
okay.
Another situation is where same game, rock paper scissors. Player A, puts in some money. They're betting I'm going to win, but I'm sending in scissors in a secure way. Player B cannot see my result, right? Maybe they use a commit reveal scheme, right? Player B just decides not going to play. What happens then? Yeah, player A just loses money, right? He can never recover it because the game doesn't end. Player B doesn't really care. How do you prevent against that? Well, you can do checking for timestamps. So you can have a situation where, okay, you add in a method, and that player A can check. It refreshes every day. And so at a limit of 3 days, if player B still hasn't submitted their move, okay, well, player A can recover their funds. Make sense? Assert, require, talked about these. Require is meant to be used for input validation, so that's on the user's part. And assert is to be sprinkled into every function. But really, things shouldn't fail on asserts, right? If things fail during an assert, something is like grievously wrong. The asserts are just there to let you know that you should reevaluate your life. Maybe don't program smart contracts. That's the only situation you should use asserts. No, seriously.
So what's like an example of when you use an assert?
Right, so it's to make sure that a calculation always stays positive, right? When you're using like funds. Like if it's gone negative, wow, how did that happen? You've like maybe not used a uint. You've used an int. So
it's like idiot proofing your code.
I'm gonna stay away from saying that, but some people would say yes to that, yeah. Right. Always make sure it's clearly visible what your modifiers are, especially public and private. You saw earlier that they omitted internal from the parity contract. Even if something is by default public, just add public in, making sure that everybody knows that this is a public function. By default, variables are private. By default, methods are public. But you just want to add that in. Add private to your variables, add public to your methods, right? There's very little downside and a lot of upside. A lot of hacks have happened just because of incorrect modifiers. All right, this is just an example. Also, don't overwrite method names like transfer. Those are default method names. You don't want to be defining your own transfer. Or send. Or revert. Send. Okay, avoid external calls. Each and every external call is a way for someone to siphon money off you. Right? Use these as little as possible. And when you do use them, make sure that the calls are to trusted contracts. Easy. Again, this section is called simple stuff. Right. We talked about these. The one we haven't talked about is called out value. Right. We've got send. We've got transfer. So send returns a boolean, true or false. That might be useful for some if conditions. Transfer reverts. And then called out value, you just don't want to use. Yeah. Revert and throw are strange. So the docs say it can be used as an alternative, even though they compile down to different bytecodes. Shouldn't matter too much for now. It'll soon be deprecated. Throw will soon be deprecated. So just keep this in mind. Okay, pragma statements always block your correct versions, right? So this is good, this is bad. What the up arrow means, the caret, is that you can use version 0.4.4 and upwards, right? And you can't really predict what future versions of Solidity will do to your contract, right? So for example, right now, all throw calls, nobody knows what's going to happen to contracts with throw calls. That allow the compiler to run them in a future version of Solidity. Okay. So testing real quick, you want to aim for 100% test coverage. That means covering every functionality of every method in your tests. We'll talk about that at a later date. And you should implement test-driven development, TDD, which just means writing your tests before you write your methods. Yeah, that avoids things like confirmation bias, things like that. Okay, I don't think we have time for an example, but it's just basically another mode of attack. Maybe go through it on your own. Okay, and then community tools you're going to be using. OpenZeppelin. OpenZeppelin, Akash mentioned earlier, is just a framework for writing safe and secure smart contracts. So it's got predefined like templates for an ERC20 token or safe math operations that you can use. So look into it. All the links are there. Oyente, it's an analysis tool for smart contracts. It's not perfect, but it'll point out some bugs in your code. SolCover measures your test coverage. So it literally tells you which methods are being tested, which lines in your code are being tested for, and which aren't. Now remember, 100% test coverage doesn't mean your code is infallible. It just means that your code is running the way you think it should, right? And if you think it should be running in an incorrect way, well, that's still on you to make sure that you test for that. Okay, and lastly, SolGraph. This is a new one, still experimental, but it kind of outlines the flow with which your contracts can run. Whether you have external calls to unknown contracts, untrusted contracts. What are your getter methods? What are your setter methods, right? What are your constant methods, etc., etc. And the last thing I'll talk about, now that I brought up constant, is that there's a recent change with constant where it's split into two. There's a modifier now called pure, and another modifier, can't remember the name of, but basically, view, right? And view is basically what constant used to be. But pure is also constant, but it's for when you're doing computation. You're not changing anything on the contract, but you're doing computation. So keep that in mind. If your constant modifiers stop working, that's the reason why. View and pure. All right. I think that's it for today. Any questions on anything?
What was view again?
So view is what constant was, but like without the computation. So it's literally just a return. All right, thanks for coming.
Hey, so with the vulnerability with